So remember that if you had a sequence AN and a sequence BN, and you knew that AN converts to A and BN converts to B, then the product here converts to A times B, right? So, and when we prove that, we use this little trick with that we're splitting the difference between this and this, right? And so I'm going to do exactly the same trick here. So I'm looking at this thing here, and so I write this thing here as f of x times g of x minus, and it doesn't really matter, where you're inserting it. So this here is like splitting the difference, and then I have to add it again. So this is certainly the same. I'm just subtracting it and adding it right back. And now I split this into two. So I write this in here. So this fraction I split into two. And the first one, I take this one here together. So, and you can factor out a g of x. You can write it like this. F of x minus f of x0. X minus x0. Right, so this is just, right, I'm just here. I'm factoring out the g of x. And then I'm left with this. This is this, and this is keeping the denominator like that. This is this part here. And then I have the other part here. But there you see that the f of x0 is factoring out. And then I have g of x minus g of x0, x minus x0, like that. But now you see that as x goes to x0, right? Well, g was continuous at x0, right? So this thing here, as x goes to x0, this thing here goes to g of x0, right? This one here. That was because g was continuous, because it was differentiable, so it was also continuous. This here goes to the derivative. And the second thing here is this here is just constant. And this here goes to the derivative. Like that. Right? So what we have proven is this here is as x goes to x0. So you see that we've proven that this difference quotient here for the product has a limit, and this is what the limit is. Right? And so this means that the product is differentiable, and this here is the derivative, and that's exactly the Leibniz formula, okay, which was this over here, this formula here. Okay, the next thing is that we want to prove the next rule is like this quotient rule. So let me prove the quotient rule. So Leibniz, right? Leibniz and Newton was the one that was responsible for calculus. And so the next thing I want to prove is this quotient rule. And so again, you have these two functions, f and g. And they are differentiable. At x0. And I'm also assuming that g here at x0 is not equal to let's just assume that g is not equal to 0 everywhere. It's never is different from 0 everywhere. And then the quotient will say that if you're looking at the quotient here, and you take the derivative of the, so it say that if you're looking at the quotient here, maybe I should, so the quotient will say that if you're looking at this thing here, this now makes sense because g does not vanish. This here is differentiable. At x0, and the derivative of this function at x0 is given by the following formula, that it is the derivative of f at x0 times g of x0 minus f at x0 times g prime at x0 divided by g squared, so g of x0 times itself. I'll write that as a square. This here again, this here is just g of x0 times g of x0. Okay. So now let's try to prove that. So we're looking at f of x, like this, at x minus, so this is the difference quotient, at x0 divided by x minus x0. Right, that's the difference quotient. And so written out, this is f of x, g of x, minus f of x0 divided by g of x0, x minus x0. So let me put this on a fraction with a common denominator. So if I do that, then this thing here is, right, so then I'm multiplying by g of x0, both in the numerator and denominator here. So I'm getting f of x times g of x0. And then here I'm multiplying by g of x in both numerator and denominator. So I'm getting this thing here, g of x. And then it becomes x minus x0, and then g of x, g of x0, like that. And so now you can write this thing here as, right, and so now you do the same trick as before. I mean, I could have gotten away slightly easier with looking at a special case of this quotient rule where f was a constant function 1. So I could do that first, and then the general case I could then get from this special case together with the Leibniz rule. But I chose to, it's most often that one do it together anyway, but if you have to do it together, you have to use the same trick that we just did. So we're using that over here. So so f of x, g of x0, minus, and then f of x0, g of x0, plus f of x0, g of x0, minus f of x0 g of x. So this is again where I'm subtracting in the denominator something and then I'm adding it back up immediately. So I have this. Like that. And so now, if you do that, then you see that, so now you can, and now you split it up again into two fractions. So we split it up. And so this thing here, but there you see that there's a g of x0 that factor out. So this is equal to g of x0, and then you have f of x minus f of x0, and then x minus x0, g of x, g of x0, like that. And for the second one, you see that there you also have something that factor out. And this is f of x0, like that. And you're getting g of x0 minus g of x over x minus x0, g of x, g of x0, like that. Right? And now, okay, so now I can make this looks nicer. I can, this one here, cancel with that. And so I can write this thing here as 1 over g of x, f of x minus f of x0 divided by x minus x0. So this takes care of this. Here I can, I will write it as, I will take this one here out, so I'll write it as f of x 0 g of x times g of x0. And then I'm left with this thing here. And what I don't love about this thing here is it's not quite the difference quotient because the order of these two is wrong. So I switch the order, but if I switch the order, then I have to pick up a minus sign. So I get minus here, and now it is g of x, g of x0, x minus x0, like that. Okay, and now you see that as x, so as x goes to x0, so now as x goes to x0, well, this one here, the function was differentiable, so it's also continuous, so this goes to 1 over g of x0. This one here just goes to the derivative at x0. This one here goes to, again, because the function is continuous, this goes to minus f of x0. And then it's what I wrote before as g squared, it's d of x0 times itself. And then this thing here goes to the derivative of x0 at 0, right? And now I can, if I want to, I can rewrite this thing here. If I want to put it back on a common denominator, then I have to multiply in the numerator and denominator by g of x0. If I do this, I get f prime of x0, g of x0, and then I get g squared of x0 in the denominator, and then here it's just those two minus f of x0, g prime of x0. And so you see that this here is exactly this formula here, this quotient rule, right? So this proves that if you take two functions, the one you have in the denominator, if that is non-vanishing, so you can form the quotient, and if each of these two functions is differentiable, then the quotient is also differentiable, and this is the formula for the derivative. Right, so now why is this already really, really useful? So, so we calculated. We already we calculated. So we started with the example of where f is a constant, right? And we saw that it's differentiable and the derivative is 0. Then the second example we had was where the function was x, and we saw that it was differentiable and the derivative is 1. Right? If you now take ax times right, so let's just take ax as the next example. This is like a constant function times this function. So Leibniz rule, sorry, if f of x is equal to a times x, where a is a constant, Leibniz rules say that the product of two differentiable functions is differentiable, and the derivative of this is the derivative of that, but the derivative of that is a constant function, so that's 0, so I don't even have to think about that. So it's just a times the derivative of the second function, but that's 1, so this here is the derivative of that. Right, so, and the next example would be that you're looking at ax plus, say, b, f of x is equal to this. Then you can use the sum plus, we know what each of these is. So you get that this one here is also differentiable, and the derivative of this function here is also just a. And you can continue like this, that if you take, if you now have a polynomial, suppose you take a to the power n. So if f of x is x to the power n, then you can think about this thing here as x times x times x times x, and you can use the Leibniz rule, right? And so if you use the Leibniz rule, so you just do it first in the case where f of x is equal to x squared. You can think about this as x times x. These are two differentiable functions. So the derivative here is now the derivative of this. So that's 1 times the other function, plus you keep this one here, and you take the derivative of that. So this is this. So this is 2 times x. Right? And so if you take this function here, using Leibniz rule, in this case, the derivative, it's differentiable, and the derivative is n times x to the power n minus 1. Right? So that's so and in fact, right, even more generally, just using the sum and the Leibniz rule, if you take any polynomial, a n x n plus a n minus 1 x n minus 1 down to the last thing is being a constant. If you take a polynomial like this, just using the Leibniz rule and the sum rule, using those repeatedly, we know that this here is differentiable, and the derivative is just like the sum of the derivative of these, so this is going to be n times x to the power n minus 1 plus n minus 1 times n minus 1 x n minus 2. And then this one here, the derivative is 0, so the last one you're getting something non-trivial for is a1. Right, so this is just using sum and Leibniz rule. Right? And so this is just using the sum plus Leibniz rule. Repeatedly. Okay. Now, likewise, if you take a rational function, so meaning that if you take something, if f of x is equal to some polynomial, a polynomial, so let's go to p of x divided by q of x. So where this here is a polynomial, and so is that. Right? So now you can use the quotient rule. Right? So the quotient rule will tell you that as long as you are looking at point where this here does not vanish, so then the quotient here is also differentiable, and it gives you a formula for the derivative in terms of the derivative of each of these two. And each of those two, they can be calculated like that. Right? So you see, it's already now we have like quite the derivative of a lot of functions, right? We have of all functions and of all rational functions. Rational functions, again, are quotients of a polynomial by other polynomial. Okay. So now the next rule that we want to talk about is the chain rule. So what is the chain rule? So the chain rule is a little bit different from those three rules here. And it is where you take the composition of functions. So the next is the chain rule. And again, this is about composition of functions. Okay, so I have a function f that goes, say that it goes from some interval a to b into another interval from c to d. And then I have a function g that goes from this interval here into R. Because g is defined, you know, like whatever the image of f, always if it's in the set, this is where g is defined. Then you have that you can form, if you take some x in here, so if x here is in a to b, then this here makes sense. And this is now an element here, so this is where g is defined, so this here makes sense. Right? And this is now what we call the composition, and we write it like this. It's important to write it in the correct order. And so this is the composition function. Okay, and the thing is that this, so now the chain rule is the following. So the chain rule is the following theorem. That if f is differentiable at x0 and g is differentiable at y0, where y0 is equal to the value of f at x0, then the composition of these two functions is differentiable at x0, and the derivative is equal to the derivative of g at y0 times the derivative of f at x0. So this is the chain rule. Right? The chain rule says that the composition is also differentiable at x0, and this is the formula for the derivative. Okay, let's try to prove that. And so that in this case, it's useful to divide up to two and the two cases to divide up to, so let me just look at the special case first, and then once we understand that, it would be clear, the general case would be clear. So let's make one assumption. So let's try to prove it. But we assume first that the derivative, I'm going to assume that the derivative at x0 is not equal to 0. So I'm assuming that first. What does this guarantee me? Well, remember that the derivative is the limit of this difference quotient. Right, so this is the limit. If this here is not equal to 0, this means that when x is very close to x0, this thing here is very close to this thing that is not equal to 0. But then it means that if you are very close to x0, f of x cannot be equal to. So if you have this here, this implies that f of x is not equal to x0 is not equal to f of x0 for x sufficiently close to x0. I'm always assuming, of course, that x is not, but x is not equal to x0. Right? So I'm going to first make this assumption. And if I make this assumption, what I get out of it is that this thing here is not equal to that. Why is this useful? Because now I can actually look at this difference and I can divide by it. Okay. So I'm going to just to make things a little bit clearer. So I have my function. So this here is f, and here I have g. Here I have x0, but under f it's taken to this, which is f of x0, but this I also will denote by y0. Right? So I'm denoting, just to make things clearer, y0 is just the value here. And then I will use f of x, I will denote by y. Okay. So now I'm looking at the difference quotient. So I'm looking at I'm looking at g of f of x minus g of f of x0. X minus x0. That's what I'm supposed to look at. And I can write this thing here as g of y, because this here I also call y, right? So you can write it like this, g of y0. And then I will write it as y minus y0, but I didn't have this in the denominator up here, so I have to multiply it back on. And then I still have to divide by like that. Right? So I can write it like this. This here I'm happy with. We'll get to this in just a second, but I'm happy with this expression. The other one, I really want to put it back in terms of f. So I'm writing this thing here. And this thing here, I really want to put it back in terms of f. So if I do that, I write it as f of x minus f of x0. X minus x0. But now you see that as x go to x0, right? Well, as x go to x0, because the function f was continuous at x0, it means that if x goes to x0, then the value at x, which is y, will go to the value at x0. So when x goes to x0, we have that y goes to y0. Right? So this means that this thing here, this here converge. Right? That's just because the function f is differentiable. So this here will converge to the derivative. So this, the second factor here is converging to f prime at x0. The first factor is, but now you see that we just argued that y goes to y0. So this is also a difference quotient, but it's a difference quotient for g. And since y goes to y0, this difference quotient here goes to the derivative of g at y0. Right. But that's exactly the formula that we wanted to prove, except that we made one assumption, that the derivative of f at x0 was not equal to 0. We made that assumption only so that this thing, number here was not equal to 0, right? And so we could kind of divide by it, right? But actually, otherwise, right? If you, for some reason, if y was not equal to y0, but right, then this formula here would still hold, right? So it's only the possibility that that y could be equal to y0. But now you see that if you were just looking at the difference quotient, g of y minus, g of f of x minus, so this is the difference quotient that is the one we really have to look at for the composition, right? And this is what we also called, this here is what we called, this thing here is what we called y0, this thing here is what we call y. And the only case we haven't dealt with is where f prime of 0 is equal to 0 and y is equal to y0, right? This here again was f of x, and this here was equal to f of x0. So this only this case here we haven't dealt with, right? But you see that if it so happened that f of x was equal to f of 0, then this difference quotient here, the denominator would trivially be 0, right? And so you want to prove, we have that if this here was not equal to 0, then we have that this is converging to the derivative. And the only case we have to look at where this derivative is 0, so we are claiming that. So the only case we're left with that we haven't dealt with is, first of all, where the derivative, so let's see, so let me just write down here clearly. The remaining case for the chain rule so the remaining case is that the derivative at x0 is 0, right? And we have already observed that if the derivative is 0, but y is not equal to y0, if this is the case, then actually g of f of x minus g of f of x0, this thing here still converge. In this case here, where this is the case, this here still converts to 0, right? So we still have the chain rule in that case if this here was not the case. The only thing we have to worry about is what if y was equal to y0? But if y was equal to y0, when we're looking at the difference quotient, this is the difference quotient after all. And so in that case, this thing here is y0, this is y0. But in that case, the difference quotient is actually 0 already. So of course, it's going to be very close to 0, right? It actually is 0, right? So you see that the remaining case, that's sort of trivial. Right? But we wanted to first exclude it because we wanted to be able to divide by this difference, right? And then once we have seen that under that assumption, it was, we got the formula we wanted, then we go back and then we say that not only, the remaining issue was, well, first of all, was the case where the derivative was 0, but in fact, the only case that was potentially a problem was when y was equal to y0, but for that, the difference quotient was actually trivially 0. Okay, so that's the chain rule. And so we only have a few minutes left, and I won't quite be able to get through all of the stuff, but I can get through one more lemma. And then I'll pick up from here next time. The notes are already posted, but so the last bit of the notes we'll do next time. So the following lemma here. So if you have a function, say from R to R, and you have that x here, x0 is a local max or min. So f is a function from R to R that is differentiable. And x0 is a local max or local min for f. Then the derivative at x0 is equal to 0. Okay. Let me remind you what a local max and local min is. So if you take a function, so a local max, similarly for a local min, if you have a function here, you have here x0, a local max means that in a neighborhood of this point, then the value at x0 is the maximum. So local max at x0 means that there exist delta greater than 0 such that that if you're looking at the interval to either side of x0, this interval, and you're looking at f here restricted to this subset, then x0 is a local max, is a max. So this means that f of x0 is equal to the max of f, where x here is in this little interval here. Oops, like that. Right. So it may not be right. So so the idea is that it's just the function may look like this, and this here is x0. So you see that in a neighborhood like this, it looks like that you have that this x0 is a maximum, but there might even be somewhere else where the value is much higher. Right? So that's a local maximum, and similarly for a local minimum. Okay, and so I won't be able to actually prove this lemma. We'll prove that next time. And then once we have that lemma, we prove what's called Rolle's theorem, and then we will use it to prove the mean value theorem. But I'll do that next time, but it's actually in the notes that I posted already.